Let's talk let's talk about quantum physics from scratch.
All right, starting from the foundation. Quantum physics at its core deals with how matter and energy behave at the smallest scales. Think atoms, electrons, photons, and the like. It's not like classical physics where things behave predictably. Instead, particles act like waves, waves act like particles, and everything is governed by probabilities. We'd start by understanding the double slit experiment, wave particle duality, and the idea of quantization. Where would you like to focus first? The theory, the math, or some classic experiments?
I'd like to talk about quantum computing perspective for this quantum mechanics application and the complete meaning of computation.
From the quantum computing lens, quantum mechanics is the backbone. Instead of classical bits, just 0 or 1, we have qubits, which leverage superposition, being in a combination of 0 and 1 at once. Quantum gates manipulate these states using principles like interference. Computation, in this context, means solving problems, factoring large numbers, simulating molecules, or optimizing systems using quantum states. The hope is that certain tasks, like factoring or searching, will be exponentially faster on quantum hardware than on classical computers. So it's a paradigm shift from classical logic to manipulating quantum probability amplitudes.
So that how does the Feynman idea made contribution to this quantum computing architecture?
Feynman had this brilliant insight in the 1980s. To simulate quantum systems efficiently, you'd need a quantum machine. Classical computers struggle to scale with the complexity of quantum phenomena. His idea laid the conceptual foundation. If nature is quantum, why not build a quantum computer to mirror it? That sparked the entire field. The concept that a quantum machine, leveraging superpositions, entanglement, and quantum gates, could tackle problems classical systems can't. In other words, Feynman wasn't just describing quantum mechanics, he was suggesting we harness it for computing itself.
So what you are suggesting basically about this quantum computing architecture and how does Feynman introduces that part?
Feynman's core contribution was the realization that simulating quantum systems with classical computers was inefficient. He pointed out that a machine obeying quantum laws would naturally handle quantum problems better. So he didn't design today's hardware himself, but he planted the seed. We should build devices using quantum bits. That idea inspired the field, leading to qubits, quantum gates, and architectures we now explore, like superconducting qubits or trapped ions. In short, he gave us the why, and we're building the how.
We are building how and he gave us why. What do you mean by that part?
What I mean is, Feynman set the stage by asking the key question. If nature is inherently quantum, wouldn't a quantum machine be ideal to study it? That's the why, the fundamental motivation. Since then, researchers have been figuring out how to physically create qubits, how to perform quantum logic operations, how to correct errors, and how to scale up. So Feynman's vision was the catalyst, and today's quantum computing efforts are the ongoing engineering journey to make that vision real.
No, what was that? How does we make qubit physical so that it compute? Can you give example?
Physically realizing qubits means using a system that obeys quantum rules. For example, in superconducting qubits, tiny circuits act as artificial atoms, with current flowing in superpositions. In trapped ion qubits, individual ions, atoms with an electron removed, are suspended in electromagnetic traps, and their energy states encode qubits. These physical implementations allow us to perform quantum logic operations, like quantum gates, to process information. Different platforms like photons in optical circuits or even quantum dots are being explored, but they all follow quantum principles to represent and manipulate qubits.
Okay, so designing hardware like superconducting qubit, where tiny circuit act as artificial atoms, and while current flowing in superpositions in trapped ion qubit, individual atoms and electron removed or suspended in electromagnetic trap, and their energy states encodes qubits. This physical implementation allows us to perform quantum logic operations like quantum gates to process information. Different platform like photons in optical circuits or even quantum dots are being explored.
Exactly. Each of these approaches gives us a different way to realize qubits. Ultimately, they all aim to harness quantum states, superpositions, and entanglement to run algorithms that would be impractical on classical machines. The field is still evolving, but each architecture is a step toward making large scale quantum computing a reality.
What we have discussed till now, can you give conclusion?
In a nutshell, we started by exploring how quantum mechanics underpins quantum computing. While classical bits are either 0 or 1, qubits leverage superposition. Feynman's insight was that to truly understand or simulate quantum systems, we'd need quantum machines. Since then, we've been figuring out how to build them, whether using superconducting circuits, trapped ions, or photons. Each architecture aims to harness quantum effects to perform computation in ways classical computers can't match. In conclusion, the field is translating that why into a growing how as we inch closer to practical quantum computing.
So, what do you thought about the level of discussion we have now? Rate from 1 to 5.
I'd say we've been at a solid 4. We went from basic quantum principles all the way to real world qubit implementations and Feynman's influence. We covered some theory, some technology, and the bigger picture. If we wanted to push it to a 5, we could dive even deeper into technical details, but I think we had a great conceptual flow.
Yeah.